So I'm going to present my second year paper. The name is Decision Making Under Time Constraint. I think I understand that this is one of the most boring names I can think of. But the problem is when I need to submit that second year paper agreement thing, I need to make a decision on the time constraint. So I have like 5 minutes and I didn't think about a proper name yet. So I just write this down. So I made this decision. It seems rational, but it's not because I'm irrational. I could think about a lot of better names, but just because of time constraint, I didn't have enough time to think about every aspect of a good name. So that's why we end up with this. So now to think about it, I think a better name would be competitive decision making under time constraint, but you will see why that's the case. So using that idea, I need to make decision under time constraint. There are two types of models that are existing models. One is the type that I call irrationally irrational, which the name is bounded rationality, which those type of paper assume players make particular types of mistakes or flaws in their reasoning. The other type of paper is it's still called bounded rationality paper, but I would refer it as rationally bounded, which means the player decides to act irrationally due to some cost of reasoning. So I think their end result is kind of the same, and the techniques they use are similar as well. I think in general, the first type uses simpler mathematics because of those assumptions of simpler reasoning, and the second usually use some complex mathematics. So what I'm planning to do with my project is that I want to do something like what the rational inattention paper did, which uses very complex mathematics to explain how people have cost of reasoning. I want to use a simpler mathematics or simpler model to to basically replicate the result to see if we can use the time constraint as some reason as one of the costs of extensive reasoning. So let's go into the first example. So suppose I want to buy a house or a condo or apartment. Then I have to decide a lot of things. But I have a time constraint, so I need to decide this in 2 days. I can think about 100 million reasons to compute my exact utility. But I need to decide into 2 days, so I cannot think about all those things. So something I may consider is, for example, price. How close is it to campus? What's the expected resale price? What's the interior design? What's the size? And what's the probability of there's a damage? What's the monthly cost, including property tax, for example? And mm, I just listed those, but I can think about other ones that are relevant. So as I said, there is a time constraint, so we should probably model this as if it's a budget constraint. So a very simple model, which I call baby toy model number one, is suppose there is one player, there are multiple, there is only one state variable that's relevant to our decision, which is the actual value of the house. And this value is dependent on infinite number of other independent variables. So the data here basically it's only dependent state of interest, and the other ones are independent variable that determines the, the state through a deterministic function f. So the other thing you notice here is the player is characterized by a model S. So the model S is basically a list of factors that the player uses in her model. So for example, S equals to this set means that the player uses this subset of independent variables when he's when she is estimating theta zero. So in particular, the absolute value of S is just the usual absolute value, which is the size of the player's model. So the size can be represented in terms of cardinality or something else if you want another kind of measure. And the other thing is the set of actions. So of course I can assume there are a group of actions, but I will just assume there is one action of implementing some action, which is when a equals to 1, and when a equals to 0 is no action. The reason that I added implementing a optimal action is because that action can be either sell or buy or something, some action that basically takes that good. So and there is the utility function g. which is a function of statistic theta zero. So the utility function here basically is as long as my model is of some reasonable size, and I choose one, I can get this utility. Otherwise, I get zero. Either if I choose zero, or I'm taking too long to make that decision. So you can probably see here there is players and one. So first it's a typo, so there shouldn't be an S here. Second, you can probably see what I will be doing. So there will be multiple players. So introducing a second example. So still the same house example. I have to decide these things. Suppose I introduce player number two. So that player think about the same thing as before. He also thinks about whether there are street gangs nearby. What's the cultural religion of the neighbors? What's the amount of escapable tax? Are there wilderness nearby? Are there broken windows or crimes? Are there housing choice voucher, which I don't really know what it is still, and what's the language skill of the security guy, which is somehow relevant as well. I think there are dot 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 and so on. There are a million other ones. So that would be the other guy. I think you see that I mentioned some of your topics. I think the reason is obvious. I think those topics are interesting. I mean, the ones that I didn't mention, it's not that they are not interesting, it's that they are not really hard to be related to buying a house. So, so then continuing doing this, there, suppose there is a third player who thinks about only one thing, whether this is deliverable. Then if this guy is one of the decision makers, for sure, every time he will get this house. But is this a good choice? And the answer is no, because there's a large probability that considering all those things, it's actually not optimal for him to choose this particular apartment or condo. So it's the less you decide, actually there's a higher probability that you make a mistake, which means there is a probability that when you should not buy and you bought it, and or when you should buy it and you didn't, and yet you did not. So that would be a model of explicit trade-off between how much you think about and how profitable that each additional variable is. So it sounds like a statistical problem, and I think you will see that it will be. So introducing baby toy model number two, there are a group of players, and those each player are characterized by the same model as before, same stage, same actions. The only difference is there's a minimum thing here, and this minimum just means among the players who choose AJ equals to 1. So among the players who want to actually buy this, only the fastest player gets to implement her action A equal to 1, obtaining that utility. So I think that this may sound straightforward, but there is a very important assumption that we make here, which is the minimum function here. You will see why. I will illustrate this using a diagram. So suppose we start at time 0, and people just start making decisions. So it's like this. They are keep going to the right. It's the longer the lines are, the longer the time they take to make that decision. So they keep doing it until some point, say player one stop, and the reason that he stopped and the game is not stopped because he chose A equal to 0. So then the game basically continues. So someone else may want to stop thinking because he thinks it's not good enough. And until some point where one player decides to buy this house. So the red line means the player choose action equal to 1, and then the game stops. So these two players, they may want to think more, but they stopped here. So you may think that this is the model that I presented is completely different because this representation has a significant problem, which is what I label potential problem number 1, because the inaction of other players actually contain information about theta 0. So if I know when the player makes that that decision of buying and not buying, so of course if we go back a bit, when those people stop, we don't actually know because if I'm making a decision, I don't know whether the other person stopped and choose to not buy or he is continuing. So I have no idea. But when I hit the point where someone actually bought it, I actually know this, so I have to stop making that decision. So the assumption So, so it's implicit that there's a problem. There is this problem here, and this problem is indeed studied by some statisticians, and it's called multi-armed bandit problem, and extended to a game theory, which there are multiple agent bandit problem, which is, there is a solution such that the player could coordinate to gather information faster by Tyler, Raddy, and Cripps. So the way I deal with this is I introduce the minimum function here, which we don't actually need to care about this, because know that in my model, each player must, if they have a model, they must evaluate this model completely. So this is only determined whether he gets a good. It's only determined by the size of the model, not when he decides to stop. So there is no stopping problem here. So we basically start with zero, and they just keep deciding until all of them stop. This is very slow, by the way. So I wait. But when a person decides to buy it, we don't stop yet. So we just let them keep going. So at the end, there may be three different persons trying to buy this thing. I only pick the first one to sell it to him. So I am assuming I'm having a model like this to avoid the potential problem that I have. So that's the end of the baby time model.